An undersized service drop on the utility side can affect the overall efficiency of the system beyond the meter. An undersized service drop increases the resistance in the circuit, which causes a voltage drop along the line. This means that the voltage reaching the meter is lower than the voltage supplied by the utility. To compensate for the voltage drop, the system must draw more current to maintain the same wattage. This increased current draw leads to higher power losses in the conductors. The combination of voltage drop and increased current draw reduces the efficiency of the system. This means that a larger portion of the energy supplied by the utility is lost before it reaches the loads. While the focus is on efficiency from the meter to the loads, it's important to note that the undersized service drop can still have an indirect impact. By increasing the current draw through the conductors, the voltage drop and power losses in the portion of the circuit from the meter to the loads will also increase. The calculation of a 25% reduction in wattage losses by increasing the wire size by one step is a reasonable approximation based on the assumptions made. However, it is important to note that the actual savings may vary depending on factors such as the specific wire gauge used, the length of the circuit, and the load profile. An undersized service drop on the utility side can affect the overall efficiency of the system beyond the meter. While the focus may not explicitly include this aspect, it's important to consider the potential indirect impact on the efficiency of the portion of the circuit from the meter to the loads. Voltage drop is a critical concept in electrical systems, representing the reduction in electrical potential, or voltage, along a conductor through which current is flowing. It's an inevitable phenomenon stemming from the conductor's inherent resistance to the flow of current. Imagine electricity flowing through a wire like water flowing through a pipe. The longer the pipe and the narrower it is, the more the water pressure drops along its length. Similarly, the longer and thinner the wire, and the more current it carries, the greater the voltage drop. Ohm's law, a fundamental principle in electrical engineering, quantifies this relationship with the equation volts equals amps times ohms. This law dictates that voltage drop is directly proportional to both the current, measured in amps, and the resistance, measured in ohms. Therefore, a higher current or a greater resistance will result in a larger voltage drop. Several factors influence the magnitude of voltage drop in a circuit. Firstly, the length of the conductor plays a significant role. Longer conductors present a greater resistance to current flow, leading to a more pronounced voltage drop. Secondly, the cross-sectional area of the conductor is crucial. Thicker conductors offer less resistance, thereby minimizing voltage drop. Thirdly, the material of the conductor matters. Materials with higher conductivity, such as copper, exhibit lower resistance compared to materials like aluminum, resulting in reduced voltage drop. Finally, the magnitude of the current flowing through the conductor directly affects voltage drop, as dictated by Ohm's law. Excessive voltage drop can have detrimental effects on the performance and lifespan of electrical equipment. If the voltage at the load is significantly lower than the intended voltage, equipment may operate inefficiently, produce less power, or even fail to function altogether. For instance, motors may overheat and burn out, lights may dim, and electronic devices may malfunction. Moreover, voltage drop contributes to energy waste, as power is dissipated as heat in the conductors due to the current flow through the resistance. To mitigate voltage drop, several strategies can be employed. Firstly, selecting conductors with adequate size, ensuring sufficient cross-sectional area to handle the anticipated current without excessive resistance, is essential. Secondly, minimizing the length of conductors by optimizing circuit layouts and reducing unnecessary wiring runs can significantly reduce voltage drop. Thirdly, using conductors with high conductivity materials, such as copper, can minimize resistance and voltage drop. Fourthly, reducing the current flowing through the circuit by optimizing load distribution and employing energy-efficient equipment can help alleviate voltage drop. Furthermore, installing voltage regulators or transformers can compensate for voltage drop by boosting the voltage at strategic points in the circuit. In electrical codes and standards, voltage drop limits are often specified to ensure the proper functioning and safety of electrical systems. These limits dictate the maximum permissible voltage drop under normal operating conditions, typically expressed as a percentage of the source voltage. Adhering to these limits is crucial to prevent equipment malfunction, energy waste, and potential safety hazards. Calculating voltage drop accurately is essential for designing and maintaining electrical systems effectively. Various methods exist for calculating voltage drop, including using Ohm's law voltage drop calculators and specialized software tools. These methods typically involve considering the conductor's length, cross-sectional area, material, current, and other relevant factors. By accurately predicting voltage drop, engineers and electricians can select appropriate conductors, optimize circuit designs, and ensure that the equipment receives the necessary voltage for proper operation. Current draw, also known as amperage draw, refers to the amount of electric current, measured in amps, that a device or circuit consumes while operating. It's a fundamental parameter in electrical engineering, indicating the rate at which electric charge flows through a circuit. Understanding current draw is essential for designing, analyzing, and troubleshooting electrical systems. Several factors influence the magnitude of current draw in a circuit. Firstly, the power consumption of the device or circuit is a primary determinant. Devices with higher power ratings, measured in watts, typically draw more current. Secondly, the voltage at which the device operates affects current draw. According to Ohm's law, current is inversely proportional to voltage, meaning that for a given power consumption, a lower voltage will result in a high current draw. Thirdly, the impedance of the circuit, which is the total opposition to current flow, influences current draw. Lower impedance circuits allow more current to flow, while higher impedance circuits restrict current flow. Current draw can be categorized into different types, each with its own characteristics and implications. Firstly, inrush current, also known as surge current, is the peak current drawn by a device when it is initially turned on. It's often significantly higher than the steady-state current draw due to the charging of capacitors or the energizing of inductive components. Secondly, steady-state current is the constant current drawn by a device during normal operation after the initial transient period. Thirdly, fault current is the excessive current that flows through a circuit during a fault condition, such as a short circuit or ground fault. Fault current can be several times higher than the normal operating current and poses a significant safety hazard. Excessive current draw can have detrimental effects on electrical systems and equipment. Firstly, it can overload circuits, causing breakers to trip or fuses to blow, interrupting power supply. Secondly, it can overheat conductors, leading to insulation damage, fire hazards, and equipment failure. Thirdly, it can reduce the lifespan of electrical components, such as motors, transformers, and electronic devices. To mitigate the risks associated with excessive current draw, several strategies can be employed. Firstly, using appropriately sized circuit breakers or fuses to protect circuits from overload conditions is essential. Secondly, employing surge protection devices to suppress inrush currents and prevent damage to sensitive electronic equipment is crucial. Thirdly, implementing proper wiring practices, such as using conductors with adequate ampacity and minimizing loose connections, can reduce the risk of overheating and fire hazards. Fourthly, regularly inspecting and maintaining electrical equipment to identify and address potential issues, such as worn insulation or loose connections, is vital. Furthermore, using energy-efficient equipment and optimizing load distribution can help reduce overall current draw and improve energy efficiency. Electrical codes and standards specify maximum current draw limits for circuits and equipment to ensure safety and prevent overloading. These limits are based on the ampacity of the conductors, the rating of the circuit breakers or fuses, and the type of load being served. Adhering to these limits is crucial to prevent overheating, fire hazards, and equipment damage. Measuring current draw accurately is essential for troubleshooting electrical problems, assessing equipment performance, and ensuring compliance with safety standards. Various methods exist for measuring current draw, including using clamp-on ammeters, multimeters, and specialized power analyzers. These instruments allow electricians and engineers to measure current without interrupting the circuit, providing valuable insights into the electrical behavior of the system. Electrical efficiency is a critical metric for evaluating the performance of electrical systems and equipment. It quantifies the ratio of useful output power to total input power, indicating how effectively electrical energy is converted into the desired form of work or output. Higher electrical efficiency translates to lower energy consumption, reduced operating costs, and minimized environmental impact. Several factors influence the electrical efficiency of a system or device. Firstly, losses within the system, such as resistive losses in conductors, core losses in transformers, and switching losses in power electronic converters, reduce efficiency. Secondly, the design and operating conditions of the system affect efficiency. For example, operating a motor at its rated load and voltage maximizes its efficiency, while operating it at significantly lower or higher levels reduces efficiency. Thirdly, the quality of the components used in the system influences efficiency. High-quality components with low losses contribute to higher overall efficiency. Electrical efficiency can be expressed as a percentage, with 100% representing perfect efficiency, where all input power is converted into useful output power without any losses. However, in reality, all electrical systems experience some degree of loss, resulting in efficiency values less than 100%. Improving electrical efficiency offers numerous benefits. Firstly, it reduces energy consumption, lowering electricity bills and conserving valuable resources. Secondly, it decreases greenhouse gas emissions associated with electricity generation, mitigating climate change. Thirdly, it extends the lifespan of electrical equipment by reducing operating temperatures and stress on components. Fourthly, it enhances the reliability and stability of electrical systems by minimizing voltage drop and reducing the risk of overheating. Various strategies can be employed to improve electrical efficiency in different types of electrical systems. Firstly, using energy-efficient lighting technologies, such as LED lamps, can significantly reduce energy consumption compared to traditional incandescent or fluorescent lamps. Secondly, employing high-efficiency motors and drives in industrial applications can minimize energy losses and improve overall system efficiency. Thirdly, optimizing transformer loading and using high-efficiency transformers can reduce core losses and improve energy efficiency in power distribution systems. Fourthly, implementing power factor correction techniques can minimize reactive power and reduce losses in electrical circuits. Furthermore, using smart grid technologies such as advanced metering infrastructure and demand response programs can optimize energy usage and improve overall grid efficiency. Electrical codes and standards promote energy efficiency by setting minimum efficiency requirements for various types of electrical equipment and systems. These standards encourage manufacturers to develop and market energy-efficient products, and they provide guidelines for consumers to make informed purchasing decisions. Compliance with these standards is essential for reducing energy consumption and promoting sustainable development. Measuring electrical efficiency accurately is crucial for evaluating the performance of electrical systems, identifying areas for improvement, and verifying compliance with energy efficiency standards. Various methods exist for measuring electrical efficiency, including using power meters, energy analyzers, and specialized software tools. These instruments allow engineers and technicians to measure input power, output power, and losses in the system, providing valuable insights into its efficiency performance.